quick? So this question is called J-Kiplo Grid Pog. Don't ask me why I called it that. Anyways, let's start reading the question. So we have this grid, and basically we want to find out the minimum number of moves required to travel from the bottom right to the top left. So for example, if we have this grid, we want to travel from over here, bottom right to top left, up here. And yeah, that's basically the entire problem. So let's think about how this works. So this problem says that again, um, we'll start at the top left corner, right? So in this case, we'll just start at like 0, 0, index 0, 0. And then from here, if we start over here, for example, we can get to this space and this space by moving 2 spaces. And then from there, here we can look at like how we can move 3 spaces. In this case, the only way we can move is over here. And then over here, we can look how we can move 2 spaces, which is just 1, and then back to 2, but that's not going to help. And then you can just keep doing this algorithm until you eventually get to this final square. And if you think about it, this algorithm is actually just BFS. So instead of like having like walls and having to like determine if you can like traverse, like determine if there's a wall between like 2 squares, it's a little bit different. Instead, this BFS is that you're going to have to, this BFS just says you're going to have to increment yourself by like a different value. So for example, if you're on this square again, you're gonna have to increment your positions by 2. So yeah, let's start coding up this problem then, because it's just a pretty simple breadth first search. And I'll get more into detail as I'm actually coding it. So let's just begin by just getting a scanner and putting our everything in C equals input.next int, and then there's C cases. And now we have, so first thing we input in each test case is N and M. So boom. Then we input the values of the actual grid over here. So int vals equals new int nm for int j equals 0, j less than m, j plus plus. And this is where we're just going to take in each row and then look at each character. So this is where we take in each row, string s equals input.next. And then for int k equals 0, k less than m, k plus plus, we just have vals jk equals s dot char at k minus 0. And we can do this because we know that all values are just going to be characters from 0 to 9. Next of all, let's keep going. Let's start thinking about how to actually do this problem. So again, as we said earlier, we're going to do a BFS. So how a BFS would work is that we have some array list of like cells we want to look through, right? So then each iteration we want to look through the cells that take like for iteration I, you want to look through the cells that have a minimum of I steps to reach it. So for example, in the 0th iteration, we just have the initial cell. In the first iteration, we have the 2 cells that take 1 step to reach it. In the second iteration, we have these 2 cells that take 2 steps to reach it, and so on and so forth. That's what we're going to keep doing. And while we go through these iterations, we can store like what's the minimum number of steps to reach any single cell. Because what we're doing here is we're just checking like every single cell that has a minimum of 1 move, then a minimum of 2 moves, then a minimum of 3 moves, then a minimum of 4 moves, and so on and so forth. So basically what we're saying is that we need two main things. First of all, we need an array that can store we need like a 2D array that can store the minimum amount of moves to travel to each cell from this top left cell. And second of all, we need an array list to store the cells we still have to look through, because for example, if we have like this 1 and 3, right, then we're going to store these 2 cells so that we can later look through them in our next iteration. So let's start. First of all, let's just create the maximum array equals new int n by m. for simplicity's sake, I'm going to fill everything with negative ones. Arrays.fill max minus 1. And then I can also just do max 0, 0 equals 0. Because it takes 0 moves to move to the first cell. We already know that. So yeah, next of all, we have to create, again, the array list of things we have to look through. So array list integer. This is called q equals new array list integer. Then we would begin by looking through zeros. So we have to add 0 first. So then after that, the actual BFS algorithm itself would just be a while loop, because while we still have cells to look through, we're going to keep looking through them. But eventually, let's say we visited every single cell that we can, then there's no more cells to look through, which means that this array list Q would be empty and we'd stop. So our while loop condition would just be while Q dot size is greater than 0. And now for each, and now we would examine Q dot get 0, right? Because when we're looking at BFS, we want to look at the first thing in our, I guess it's kind of like a key in our queue. That's why I'm calling it Q. So then we look at just Q dot get 0, and then we look at, and so like let's say this Q dot get 0 equals 1, and then we look at the possible places you can get from Q dot get 0. In this case, it would be like these 4 cells with 0, 1, 2, 3. Then you would check if getting to those cells using this, if getting to those cells would be like if we visited those cells already. Because if we have visited those cells already, that means that this wouldn't be optimal, because again we're visiting the cells, because again we're like iterating by like the lowest minimum amount of moves to move to a specific cell. So if we've already visited something, then it's probably going to have a lower amount of moves to move to it than we have right now. Than we would have right now. So then, yeah, we would so basically we would just check all 4 of these cells, check if we visited before, and if we haven't, we would just visit it, update the minimum amount of moves to actually move to it, and then add it to our queue. And we're not going to add things to our queue that we've already visited before, because then we would have already added them to the queue when we visit them for the first time. So let's see how this works. So first of all, I'm going to create an auxiliary array. Auxiliary, blah. This is just going to be to make things a little bit simple. What this does is, instead of me having to do like 4 cases, I can just do like a for loop among this array to check instead of doing like the 4 different cases, programming 4 entirely different cases to check like if these 4 cells are like in bounds and not visited, I can just do like the current cell plus whatever changes we have here, which is a lot simpler. Then, also, by the way, our array list is going to have so our array list is going to be having 2 different, supposed to be containing 2 different values. So I'm just, instead of creating like an array matrices, because I don't feel like doing that, let's just have xy correspond to xm plus y in this array. And remember, this is going to be distinct because y has to be less than m. So then to find x, this would just be this converted value divided by m. To find y would be the converted value mod m. So basically, when we're adding a cell to Q, we would just add it in this form instead of just in the xy form. So let's start doing this actual algorithm again. So for int j equals, so we have to look, so what we're going to have to do first is look through the 4 cells that's adjacent to like the 4 cells we can move to from the current cell we're at. So j less than changes dot length, and then j plus plus. So yeah, this can show us like the 4 places we can move. So then let's just let int val is going to be equal to vals q dot get 0 divided by m, and then q dot get 0 mod m. So what this does is that it just gets like the current value. Like for example, if we're currently on this cell, it just gets the value. Remember that this just goes back to the XY format. So this is like val's xy for the current xy coordinate we're on. Then we have to check again if our new cell satisfies two things. First of all, if it's in bounds. So I'm going to write a new method for that. If it's in bounds, and if it's if the max and if the new max and if like the actually, why am I calling this max? It should be min technically. Whatever. Okay, and if the minimum amount of steps to move to, and if we haven't visited that cell before, which means that max of whatever the new cell is would be -1 because we haven't updated it with something, which we would do if we have visited it before. So basically the second part is going to be max q dot get 0 divided by m. Remember, that's the x coordinate, and then we update the x coordinate, and then the change to the x coordinate would just be plus val times changes j 0. This is just because val is going to be like the weighted value, and then changes j0 is just going to be like how much the x coordinate changes in each case. So for example, if we're at here, then the x coordinate would just subtract by minus val. So for example, if we're like at this 2, then the x coordinate would subtract by 2, and we get to the cell we could get from there. And similarly, the y value would just be q dot get 0 mod m. Remember, that's the initial y value plus val times changes j1. So again, this changes just illustrates like in each case, like proportionally how much does the x or y change. So if this is true, I'm going to write this inbounds method later, but if this is true, then we have that first of all, we would update the minimum amount of moves to reach this new minimum amount of like how do I say it? Minimum amount of moves required to reach this new thing. So this new index. So in this case, it would just be I would just be like this thing is equal to max of q dot get 0 over m q dot get 0 mod m. So this is again the original index plus 1. Then after that, I would add again, after you visit something for the first time, we should add it to our queue. So then we would just, because again, if we haven't visited already, it would never have been in our queue. So we add it to our queue. So q dot add changes j0 times val times m. Again, over here, we're going to have to add the converted version. So in this case, it's going to be like this thing. It's going to be like this times m plus this. So it would just, so since this times m plus this just cancels out to q dot get 0, we can just do like q dot get 0 plus, and then val times changes 0 times val times m, and then plus val times changes j1. And this is basically, and we're just going to add this. So then next of all, after we look through every single one of, so we're going to look through all these, right? So we're like all of these 4 cases. After we look through these 4 cases, we have nothing left to do with this original like thing in queue because it's pretty useless. We already know the minimum amount of moves required to get to it, and the minimum amount of moves required to get to all of its adjacent things, all of its neighbors. So we can just q dot remove 0, move the 0th cell, and then we can just keep iterating over and over again. And that sounds pretty good. And then in the end, we would just print out max of n-1, n-1, because that's the optimal amount of moves to move to this position. Now there is one thing I haven't done yet, and that's to, of course, figure out how the inbounds thing works. It's actually pretty simple. So what this inbounds thing does is that it makes sure that the thing we're visiting is inbounds. For example, if we're at this 3, then going here is inbounds, but if we go left or we go up or we go down, that's not going to be inbounds. And I want to just create a quick method to do that. So boolean inbounds, and this would just be an n and m. So we just take this n and m, and then we can take, let's see what we need here. So we need we have the current we would enter the current like q dot get 0 because that's like the current x value. So int cur. Then we would have the change. Then we have the change in x and change in y. So let's just say int x, int y. So the change in x would just be val times changes j0. Change in y, whoops, would just be val times changes j1, as we said earlier. And again, this can be positive or negative because, again, you have positive, negative 1 here. So basically what this does is now, so if the new x, which is just cur over m plus x, because remember cur is going to be in this format. So the previous x is just dividing cur by m. So this is greater or equal to 0, and it's less than m. Cur m plus x less than n. Then it would be in bounds. Then we have to check if the new y coordinate's in bounds. So if cur mod m, remember that's the old y coordinate, plus y greater or equal to 0, and cur mod m plus y less than m, then we can just return true. Otherwise, if it doesn't satisfy both of these, then we have to return false. So yeah, we've now I think we finished this code now. I think we've done everything that we wanted to do. So let's just try running and see if it works. There's a compile time error, unfortunately. Let's see what happens. So the bad operand time for binary operator and. So what's up with this? So remember that, again, this is going to be a Boolean in bounds. Then we have if in bounds, and then all these things, which should be correct. And, oh, I forgot to say max is equal to -1. Because, again, this is going to be like, this is just going to be the minimum amount of moves required to move to the new cell that we're going to visit. But of course, if we want to visit it, then the minimum amount, then we can't have visited before. So it has to be -1, which is what we just default fill it with. So let's try this again. Says no response on standard out. Interesting. Let's see what's up with this now. So there's a runtime error on line 23. So 23. Oh, I didn't put max j. Yep, that's a small slip. And now it works. Again, I'm just putting max j because we can't fill like a 2D array. We can only fill like a 1D array, I think. So let's just submit this, see how it goes. And it passes both test cases. So yeah, that's the question. Does anyone have any questions or issues or anything regarding this problem? If not, I'll hand it off to question 4, which is William. Who is it again? Daniel. Right?
Yeah.
All right.